In this video, we're going to do some more examples of the integration by parts technique. So the first example we're going to do is the integral of x squared e to the 3x dx. This is a problem very similar to one that we did in the previous video, which was x times e to the x. Here we have some slight differences. It's x squared instead of x, and it's e to the 3x instead of e to the x. The thing that matters most about this problem is the square. That's the thing that makes it more difficult. This is a product, and very often when you see an integral that's a product, you're going to think maybe integration by parts is the right technique. The first thing you should always ask yourself is, can I do this using a substitution? Because that's usually easier. Not always, but usually. In this case, there's not really a substitution you can do because there isn't much in the way of composition. You do have a 3x in an exponent, but that doesn't help you much with that x squared here. So instead, we're going to use integration by parts. The x squared is going to be our u, and everything else is going to be our dv. So let's try that. U equals x squared, and then dv is equal to e to the 3x dx. So if u is equal to x squared, then du is the derivative 2x dx. What about v? In order to find v, we need an antiderivative of e to the 3x. So if I tried to let v be equal to e to the 3x, then that wouldn't quite work, because the derivative of this v is 3e to the 3x dx. And that won't work because of that 3 there. So what I need to do is I just need to put a 1/3 in front, because then I'm going to have 3e to the 3x dx over 3, and those cancel. So as long as I have that 1/3 there, this will work as my v. So now we want to use the integration by parts formula. So it's u times v minus the integral of v du. Now we just plug in. U is equal to x squared. V is equal to 1/3 e to the 3x minus the integral of v, 1/3 e to the 3x, du. And du is 2x dv. So u times v minus the integral of v du. The first part of this we don't really worry about. We can simplify it slightly just by writing it as 1/3 x squared e to the 3x. That's not so much simplification as just reordering it. Then we have minus, and you can take out the 2/3. Then you have the integral of x e to the 3x dx. Now this one is essentially the same as the one we did before, x times e to the x, but now it's just got a 3 in the exponent. This one we can solve using integration by parts. And we let u be equal to the x, and everything else is the dv. So we're going to have u equals x, dv equals e to the 3x dx. Well, if u is equal to x, then du is the derivative, which is just 1 times dx. dv is e to the 3x dx, but that's the same as the one that we had before. So we already know what the antiderivative is. 1/3 e to the 3x. Now we want to use our formula again, but we have to be a little bit careful. So we leave the 1/3 x squared e to the 3x alone. Then it's minus 2/3 times this integral. We're going to use integration by parts to evaluate this integral, but you must always keep in mind that whatever the result of that integral is, you have to multiply all of that by a negative 2/3. So this is going to be negative 2/3 times, so I put a bracket here. Then it's going to be uv minus the integral of v du, like so. But make sure all of this expression is inside the bracket, because you have to multiply the whole thing by that negative 2/3. So we have 1/3 x squared e to the 3x minus 2/3 times, and now we do u times v, so it's x times v is 1/3 e to the 3x minus the integral of v, which is 1/3 e to the 3x, times du, which is 1 dx. So this is now given us another integral, but this integral we don't need integration by parts. That has an elementary antiderivative. Let's just simplify this a little bit. 1/3 x squared e to the 3x. There's not really anything you can do with that. But now we have 2 over 9 times x e to the 3x. That's 2/3 times 1/3 gives me the 2 over 9. But now I have a plus. Minus a minus gives me a plus. So it's going to be 2/3 times 1/3 is 2/9 times the integral of e to the 3x dx. And this has an elementary antiderivative, which is something we've already computed, 1/3 e to the 3x. Well, plus a constant of integration, of course. So the answer ends up being 1/3 x squared e to the 3x minus 2/9 x e to the 3x plus, and now it's 2 over 9, but you have to multiply by that 1/3, so it's going to be 2 over 27, e to the 3x plus c. And that's our answer. You can, of course, compute the derivative of that to make sure that you have the right antiderivative, and sure enough, you will get what you started with, the x squared e to the 3x. We had to use integration by parts twice because of the 2 in the exponent on the x. If that were an x cubed, we'd have to do this 3 times, or if it was an x to the 4th, we'd have to do it 4 times. But the process is the same. You just have to do it again and again and again in those circumstances. There's something related to this problem that I want to warn you about. There's a little mistake that you can fall into if you're not careful. So let's just have a little word of warning here. This problem, let's rewrite it. X squared e to the 3x. That's what we're trying to integrate. X squared e to the 3x dx. After the first integration by parts, we ended up with this expression here. I'm just going to copy and paste it. Copy and paste. There we are. Okay, so after you do one integration by parts, so that's what we use to get here. Integration by parts. You end up with, let me just rewrite it without all of the u's and v's and whatnot. So I'm going to write this as 1/3 x squared e to the 3x minus, and now I'm going to take out that 1/3 and I'm going to take out the 2. So we'll have 2/3 integral, but I'm just going to leave this e to the 3x times x like so. Okay. The reason I'm going to do that is because you might be tempted to just let u be the first thing that you see, and then let dv be everything that's left over. Oh, excuse me, this should be dx. dx. Oh, that means that we made a mistake up here a little ways. Let's just fix that now. dx. Okay. So, here's the thing you have to be careful of. If I just let e to the 3x be u, because that's the first thing that I see, we're going to end up with a bit of a problem, and the best way to see that is to just do it. So u is equal to e to the 3x, and dv is equal to x dx. So du is the derivative. So we're differentiating now. So it's e to the 3x times what's in the exponent. So you end up with 3e to the 3x dx. And v is an antiderivative, so it's going to be x squared over 2. So let's put this into the formula. So we're going to have 1/3 x squared e to the 3x minus 2/3. And again, let's put a bracket here. And we write uv minus the integral of v du. That's the integration by parts formula. Now we just fill in the blanks. So it's 1/3 x squared e to the 3x minus 2/3 times, so now we have a u times v, e to the 3x times v is x squared over 2 minus the integral of v, which is x squared over 2, times du, 3e to the 3x dx. Okay, now let's simplify this a little bit. So we have 1/3 x squared e to the 3x minus, now I'm going to do this minus 2/3 times x squared over 2. So we're going to have, let's just write it out, minus 2/3 times x squared over 2 e to the 3x. And now we're going to do that minus 2/3 times this integral. So it's going to be minus a minus is going to give us plus 2/3 integral of x squared over 2 times 3e to the 3x dx. Well, the first thing to notice is that 2 is going to cancel with that 2. So you're going to have 1/3 x squared e to the 3x minus x squared over 3 e to the 3x plus, well, this 2, that 2 cancels with that 2, and this 3 cancels with that 3, and what are we left with? The integral of x squared e to the 3x dx. These two terms are the same, so they cancel, giving you 0. And this is the integral we started with. So it's the integral from the start. So what we've shown is the integral that we started with, which is right here. We've shown that the integral of x squared e to the 3x dx is equal to the integral of x squared e to the 3x dx, which is true but also useless. What happened here was that we accidentally undid during the second stage what we did to begin with in the first stage. So in the first step here, in the very first step, we let u be equal to x squared and dv equal to e to the 3x dx. So if u is equal to x squared, then you differentiate that to get du, and dv you integrate it to get v. But notice that in our second step, which is right here, we picked u to be 3 to the x, or rather e to the 3x, which you then differentiate. So we got that e to the 3x by first integrating 1/3 e to the 3x. So you find the antiderivative in the first step, and then in the second step you differentiate the thing that you found an antiderivative of, well, rather, you differentiate the antiderivative and you get back to the start. Similarly, we started with u equals x squared and we differentiated it, and that gave us 2x dx. So you started with x squared and then you differentiated it, and then you picked that to be your dv, and then you anti-differentiated it to get back to where you started. So you have to be careful when you're doing these problems. If you have to do integration by parts more than once, you have to be consistent. Whatever you pick to be your u, in this case it was x squared, during the next step it needs to also be the polynomial term. So if we go up to where we did this problem earlier, in our first step we picked u to be the polynomial and dv to be the exponential. In the second step, again, you pick u to be the polynomial and dv to be the exponential. So as long as you're consistent in that way, you shouldn't encounter this problem where you end up undoing everything that you did and just ending up with what you started with. Our next example will be example B. And this will be the integral of sine of x times cosine of x dx. There are actually several ways to do this problem. You could use substitution. You could also use a trigonometric identity. But the way that we're going to do it is using integration by parts. This is a product of two trigonometric functions, so there's no immediate reason to choose one to be u and the other one not. So I can, for example, choose u as sine of x and dv as everything else. But it would be just fine if I picked u to be cosine and dv to be sine of x dx. That would work just as well. Let's let u be equal to sine of x. and dv is equal to cosine of x dx. So if u is sine, then its derivative, the derivative of sine, is cosine. And then we have the dx there. Well, what about v? Well, we want an antiderivative of cosine. Well, an antiderivative of cosine is sine of x, because as we just mentioned, the derivative of sine is cosine, so the antiderivative of cosine is sine, or at least an antiderivative of cosine is sine. All right, so now we want to use our formula, so it's u times v minus the integral of v du. Now we fill in all of the parts. This is integration by parts after all. Well, we found all of the parts and we just need to put them in place. U is sine of x times v is sine of x again, minus the integral of v sine of x times du is cosine of x dx. So this is sine of x quantity squared, which I'll write like that, minus the integral of sine x cosine x dx. Now, one thing that you might notice is that the integral that we have here, the integral of sine x cosine x, that's the thing that we started with. So we started with sine x cosine x in our integral, and now we have the same thing. Now you might be worried that we fell into that pitfall that we fell into in the previous example when we were talking about the warning. But that actually didn't happen here because we're actually, believe it or not, in good shape because here we have a minus sign. Let me just rewrite this equation. The left side is the integral of sine of x cosine of x dx equals the right side, which is sine of x quantity squared minus the integral of sine x cosine x dx. This integral is the thing that I want to find, but it appears on both sides. But what I can do is I can add the integral to both sides. So I can add the integral of sine x cosine x dx to both sides. Then on the right side, the terms cancel, but on the left side they double up. And you end up with 2 times the integral of sine of x cosine of x dx. And that's going to equal the quantity sine x, that quantity, squared. Now at this point I need to put in a plus c. On the left here I have an indefinite integral, so that means I'm going to need a constant of integration. In the previous line I didn't need a constant of integration because I had an indefinite integral on both sides. But now I only have an indefinite integral on one side. So on the other side I need to put that plus c. Anyway, we're almost done now because here we have the thing that we wanted to find. So we want to evaluate. Well, you know, I say evaluate, but what we really want to do is we want to find the value of this thing. And that's really what we're doing. We're not actually evaluating it because all I have to do is now solve for the unknown quantity. That is, divide by 2. If I divide by 2, I have the integral of sine of x times cosine of x dx is equal to 1/2 of whatever's on the right side. So it's going to be 1/2 times the sine of x quantity squared plus a c. I don't have to divide the plus c by 2 because c is an arbitrary constant. An arbitrary constant divided by 2 is still an arbitrary constant. But the important thing here is that now we've found our antiderivative without actually even evaluating the integral. That doesn't mean that we didn't evaluate integrals because we did compute antiderivatives. If we look back, we did compute an antiderivative at the start. We also computed a derivative. That's the whole point of integration by parts. You do things piece by piece or part by part. And in the end, you end up with the answer. Sometimes it seems to sneak up on you, like in this case. We ended up adding our integral of sine x cosine x dx to both sides. So you had 2 times the unknown quantity is equal to the square of sine x plus a constant of integration. Then you divide by that 2, you solve for the unknown, and that gives you your answer. And that's how you evaluate that problem. For our next example, let's take inspiration from what we just did. Our answer here was 1/2 sine x quantity squared. So just for fun, let's integrate sine x quantity squared. So this will be example C. The indefinite integral of sine of x quantity squared dx. Now there are different ways to do this problem. The easiest way is probably to use a trig substitution, not a trig substitution, a trigonometric identity. However, let's do this one using integration by parts. Now, at first you might think that seems like a strange thing to do because it's not a product, but actually it is a product. It's the integral of sine x times sine x dx. So there is a product here, and I'm going to let u be equal to sine, and I'm going to let dv be sine of x dx. So u is sine of x, and dv is sine of x as well, sine of x dx. All right, well, if u is sine of x, then du is the derivative, which is cosine of x dx. And now we need an antiderivative of sine, but that's going to be minus cosine now. This is very similar to the previous problem, except we just have 2 sines instead of a sine and a cosine. So this is going to be u times v minus the integral of v du. So that's sine of x times v, which is negative cosine of x, minus the integral of v, which is negative cosine of x, times du, which is cosine of x. All right, well, let's just simplify this a little bit. It's minus sine of x, cosine of x, minus a minus is plus the integral of cosine of x quantity squared dx. And now we've ended up with something which looks very similar to what we started with. We started with sine, and now we have, or rather sine squared, and now we have cosine squared in our integral. You could try using integration by parts again, but what you'd end up doing is you'd end up canceling out this term, and you'd just end up with the integral of sine x quantity squared. That's that pitfall that we talked about earlier. Instead, we're going to use a trig identity. This is minus sine of x cosine of x plus the integral. Well, what is another way of writing cosine squared? Well, using the Pythagorean identity, we can write this as 1 minus sine x quantity squared dx. Why does that help us? Well, let's look at the start. At the very start, we had the integral of sine of x quantity squared dx. And we showed that that was equal to minus sine x cosine x plus, well, this is the integral of a difference. So I can write that as the integral of 1 dx minus the integral of sine x quantity squared dx. So what I've done here is I've taken the integral of the difference and written it as the difference of the integrals. So let me just put a brace underneath that one so you can see that they're the same thing. Well, what have we done here that's so good? Well, on the left side, we have the integral of sine squared, and on the right side, we have minus the integral of sine x quantity squared. So we can do the same thing that we did before, where we add the integral of sine quantity squared to both sides. Sine x quantity squared dx. So on the left, we're going to end up with 2 times the integral of sine x quantity squared dx. Whereas on the right, these 2 terms cancel, and we're left with minus sine of x cosine of x plus the integral of 1 dx. But the integral of 1 dx, that's something we know. That's x plus a constant. So what do we end up with? We end up with 2 times the integral of sine x quantity squared dx is equal to minus sine x cosine x plus some constant. And what do you do next? You divide by the 1/2, and that will give you the answer. So the integral of sine x quantity squared dx is equal to minus sine x cosine x plus x divided by 2, and then plus a constant. Now, as I mentioned at the start of this example, this is not the best way to do it. The easiest way, so easier method, is to use a trig identity. We started with sine x quantity squared. There's a trig identity that you can use. That's equal to 1/2 1 minus cosine of 2x. This is something that's much easier to integrate. So the integral of sine x quantity squared dx is equal to the integral of 1/2 1 minus cosine 2x dx, which we can write as, if you want, as 1/2 times the integral of 1 minus cosine 2x dx. So this is 1/2, and now we want to integrate each of these terms. Now the antiderivative of 1 is simply x. And what about this thing? Well, there's a minus sign in front here. So it's minus, and then we want the antiderivative of cosine. Well, the antiderivative of cosine is sine. But because there's a 2 in here, we have to divide by 2, like that, plus a constant. So this is equal to 1/2 times x. Well, there's no point in me just rewriting the same thing. This is your answer. 1/2 times x minus sine of 2x over 2. Now this term right here, if I differentiate that, the derivative of sine is going to give me the cosine, but I have to multiply by the derivative of that 2. That's why there's a 2 down here as well, to compensate for that 2 that you get using the chain rule. The derivative with respect to x of sine 2x over 2 is going to be cosine of 2x times 2, and then you have that 2 in the denominator. So those are going to cancel and just give you your cosine of 2x. At any rate, this is your answer. 1/2, I guess I am going to just rewrite it out again, x minus sine of 2x over 2 plus c. Now, this might not look immediately the same as what you had before, but you can use a trig identity on that sine of 2x. Sine of 2x is equal to 2 times sine of x cosine of x. So if you plug that into here, these 2's will cancel, and then you'll end up with exactly the same thing that we had before. Let's do one more example. So this will be example D. This is e to the x sine of x dx. This problem is going to end up being similar in nature to the types of problems we've been doing. The issue with the problems that we've been doing and this one is that you have functions that when you differentiate them, you get something that's basically the same. So if you have a sine times a cosine, then when you integrate one, you get the other. When you differentiate one, you get the other. Here, you're going to have something similar. In this problem, we have an exponential and a trigonometric function, and there's no real way to choose one of these over the other to be u. I usually pick the first one to be u, so I'd pick u to be e to the x, although there's no reason to. And then dv is sine of x. So u is e to the x, dv is sine of x dx. So here's where the issue comes up. When I differentiate u, I get du is the same thing, e to the x dx. When I find an antiderivative for sine, well, that's going to be minus cosine of x. That isn't the same, but it's no simpler. So none of these two have simplified in any way. So when you use integration by parts, uv minus the integral of v du, you don't really gain anything. So you're going to have e to the x times v, which is minus cosine of x, and it's going to be minus the integral of v, so minus and minus is plus, cosine of x du, which is e to the x dx. We're going to have to use integration by parts again, but you have to be a little bit careful. If you pick the first one to be u and the second one to be dv, you're going to just end up undoing exactly what you did because you differentiate cosine, and that's going to give you your sine term back. And you integrate e to the x, and you're just going to get back your e to the x. So you want to be careful not to make this choice that we have indicated here. That's a bad choice. So instead what we're going to do is we're going to just swap their order. Now you don't have to rewrite this to swap their order. You can just assign u to be equal to e to the x. But I like to write it this way just so visually it's easier to look at it. It's easier to look at it and say the first one's going to be u and everything else is going to be dv, because I can underline it since the cosine of x is next to the dx. So we have u is e to the x, and then dv is cosine of x dx. Now we're following the convention that I told you to follow. If you do integration by parts more than once, then whatever your u was to begin with, that gives you a du, and that's your new u. We had a dv that was sine that gave us a cosine, well, negative cosine, but a cosine term. So our new dv is that cosine. So whatever your previous dv was, it gave you a v, and that's your new dv. So the derivative of u is, again, e to the x dx. And then the antiderivative, or an antiderivative for cosine, is sine. So once again, we want to use our integration by parts. So let me rewrite the integral e to the x sine of x dx. This is equal to minus e to the x cosine x plus, and now we're going to have uv minus the integral of v du, just like we always do. So we'll have minus ex cosine x plus, what is u times v? U times v is e to the x sine of x, minus the integral of v, which is sine of x, times du, which is e to the x du. And notice that this integral is the same as the one that we started with, just in the opposite order. But that's okay because there's a minus sign here. So we do what we did before, and you just add this to both sides. Sine x e to the x d. Oh, that's supposed to be a dx right there. Dx. And on this side as well, you add the integral of sine x e to the x dx. Now on the left, those two are the same, so you end up with 2 times the integral of sine, well, let me just write it as e to the x sine of x dx. And this is equal to minus e to the x cosine x plus e to the x sine of x. And then these two terms cancel. Now on the left we have an indefinite integral, so on the right, since we don't have an indefinite integral anymore, we have to do a plus c. We didn't have to do that before because there was an integral there, an indefinite integral. But without it, we have to put the plus c. And just like before, we divide by 2, so you have the integral of e to the x sine of x dx is equal to minus e to the x cosine of x plus e to the x sine of x, all of this divided by 2, and then just tag on your constant of integration.